All right, hello, welcome to the Welcome 1 Exam 2 review. My name is Frank. I'll be leading this review. Alright, so for Exam 2, it's really just it's the chapters that's gonna be covered is chapter 6 and 7. Yeah, so chapter 6 talking about alkyl halides, halogenation, substitution, and elimination reactions. Alright, so alkyl halides, essentially they're just hydrocarbons bonded, or halogens bonded to hydrocarbons. An important thing you need to know is that they are the bonds for um, the individual carbon halogen bond are polar, um, and the electronegativity increases when you look at the periodic table. It's from bottom to the top, and then from left to right. So the more electronegative is in the top right. Let's see. All right, so for chlorination, it's when you use H2, it's when you use Cl2 and light or HV. And important thing is that it's not selective. You can attach it anywhere. All right, so the link has been posted. So yeah, so for this one, cyclohexane, the Cl2 can attach to any one of these 6 points. Um, However, with bromination, it's highly selective, meaning it's going to be slower because it has to attach to the most stable position, that being tertiary being the most, secondary, and then primary. You also have to consider resonance. So in this example, these two positions would be the which will be where the bromine will attach because of these resonance. No, you can also for this one you use Br2 plus HV or NBS plus HV. They work. They do the same. They do the same thing. Here's the actual mechanism. So when with light, it brominates, or it takes out a radical for the bromine, which will get a hydrogen, um, leaving behind a single radical on the um, intermediate. And this is where you determine if it's stable or not, because the radicals are more stable when it's tertiary, and then it just grabs another, it grabs the bromine from Br2 to make the final product. All right, so then next reaction is going to be SN2. It's just where the X would be here would be just any living group really. Usually it's going to be halogens, but the nucleophile that you're given will just replace it. Um, yeah, liquid living group can be any electron withdrawing or any molecule that will be stable after they leave. This reaction is a concerted step, meaning it's a one-step reaction. So as it attacks the carbon, the leaving group leaves at the same time. That's what it means. It also does a backside attack, meaning the stereochemistry will have to change. You need a strong nucleophile to be able to perform this reaction, and tertiary cannot do SN2 due to steric hindrance. And another thing is you need a polar aprotic solvent, and I'll explain that more later. All right, so you have a nucleophile here. It will attack this electrophilic carbon, and at the same time, it will kick out the bromine. Here's the list of strong nucleophiles and weak nucleophiles. Obviously, the stronger ones will react faster. You can see here that the strong ones are usually um, molecules that have a negative charge already, and the weak ones are more stable, such as this one right here. This is moderate, but because we have resonance with this carbonyl, the negative charge is stable. So essentially, the strong nucleophiles are strong because their negative charge are localized to are more localized, and also strong nucleophiles can also be strong bases, but it doesn't work the other way. So the difference between basicity and nucleophilicity is basicity is just moving hydrogen, and then nucleophilicity is just replacing a leaving group. Here, the trend for nucleophilicity is from top left or top right down to the bottom left. For basicity, though, it's going to be from here, bottom right, to top top left. All right, and here's the effect of solvents. So the reason why polar aprotic solvents increase nucleophilicity is because they do not um, stabilize the nucleophile kind of like this. It basically, with polar protic solvents, they have hydrogen bonding, which can attach to the nucleophile, preventing it from attacking as fast. You'll think of it that way. These polar aprotic, they don't have the capability of hydrogen bonding, as well as polar protic. So these would be better solvents for SN2. Moving on to SN1. An important thing here is you have a carbocation intermediate. That's where you make the leaving group leave first, and then here we don't have stereochemistry because it's not a one-step reaction. Right, so you make the leaving group leave first, and then the next step would be to attack the nucleophile, and then from there you basically do proper workup where you remove any excess charges by removing hydrogens. With SN1, it is kind of the opposite with SN2, where it favors tertiary, but you cannot do SN1 with methyls. You have to look at the stability of carbocations. Um, it may do rearrangements such as hydride methyl shift, and here in this case, you need a polar protic solvent. Another thing is that sometimes they give you AgNO3. That's usually going to give a SN1 product. Here's a quick review on rearrangements. hydrate shift, moving hydrogens, adjacent hydrogens to make a more stable cation. Methyl shift is just moving methyls to get a stable carbocation. But it has to be adjacent methyls. Yeah. Here are the differences between SN1, SN2. All right, and so moving on to E1, so it's kind of like SN1. It is a two-step reaction, meaning you have to make a carbocation intermediate first by removing the leaving group. With elimination, instead of substituting the reagent, you make a double bond. For here, we need to have a base or a nucleophile that can act like a base. So the mechanism for this is the leaving group leaves, and you get a carbocation, and then the base will get a hydrogen, and the lone pairs or the bonding pairs that gets left behind will move to this bond, um, making a double bond to neutralize the positive charge. Right, and then Zaitsev product. So whenever you do elimination reaction, usually the Zaitsev product will be favored. So what that means is the double bond with more substituents will be more stable. So, for example, for this one, if it has four groups, it would be a lot more stable if it's like three, and so on. And then on the other hand, is the Hoffman product. So the only way you would use the Hoffman product is you have a bulky base or a bulky leaving group. So this one, the major product would be the Hoffman product right here, which only has two substituents, whereas the minor has three. And this one, same thing. This is a really bulky leaving group, and so it will do the Hoffman product. Here are all the common bulky bases that people usually use to do E1. And so another thing that you know is that E1 SN1 can both happen because they form in the same conditions, where here in this case you have a base here, but this is also a weak nucleophile. That's why it can attach to the substrate. And then so the other reaction, E2, kind of like SN2, where it's a one-step reaction. You need a strong base. You also need a anticoplanar hydrogen to form that double bond as the leaving group leaves. And here it favors tertiary, and then secondary, and then primary. So no, it doesn't matter. So the solvents are really just for um, just for substitution reactions. Mhm. All right, so here, this is anticoplanar. Well, yeah, assuming this anticoplanar, the hydrogen and the bromine, it will take this hydrogen and this single bond will move on to this other single bond, making a double bond, and as a result, the bromine will leave like that. Another reason why you can't do SN2 here is because this is tertiary. This carbon is tertiary, so it's sterically hindered, so it's easier for it to do E2. All right. Here's the anticoplanar mechanism. Um, as the hydrogen leaves, um, this uh, double bond will want to form a bond with the other, like the lobe of the other pi bond, and so because this is a good leaving group already, it doesn't care if it leaves, and so that's how you get the double bond. If it wasn't like if it was not anticoplanar, it has this kind of weird angle, so you can't really form a double bond that well because of the repulsion. Right, and then so for cyclohexanes, um, E2 it only happens when they are in the axial position. Um, yeah, because if it was equatorial, kind of like this, they're not really they're not really anti-parallel with each other. Like they're not on the same plane. So that's why axial, where they're one is pointing up, one is pointing down. You can easily do um, an E2 reaction. Also, I don't know if I don't think I included it in the slides, but if for SN2 on cyclohexanes, it has to be in the axial position as well. Because if it was an equatorial, there's not really much room for backside attack, so it has to go axial. So because when it's axial, there's enough room to do a backside attack because it's not pointing um, towards like the rest of the molecule. All right, and here's the differences between the two. Um, yeah, so here you need strong base. Here you just need a base really. And what you said about the solvent, I mean, the aprotic part, that's only for substitution reactions. Yeah. All right. So when should you use substitution? When should you use elimination? Um, Look at your reagents. If it's more of a nucleophile, then most likely it's gonna be substitution. Also look at your leaving group. If it's primary, it's likely to be SN2. If it's tertiary, um, it could be elimination or SN1. Bulky bases, if it's anything that's bulky, it's not going to be a second order substitution. Also, if it's because strong nucleophiles can also be strong bases. So if you have strong nucleophile and a strong base, and you have, let's say, I don't know, secondary um, leaving group, so you can really tell between the two. As substitution will usually be more faster than E2. Um, that's without heat though. Um, But if it says that if you see like a triangle anywhere, and then you don't know if it's whether substitution or elimination, usually high temperatures or addition of heat will favor um, elimination. That's because double bonds are more stable in when it's hot. All right, and so the next chapter is about really about alkenes. Alkenes just double bond hydrogens or double bond carbons. Remember, they cannot rotate, and so yeah. So for nucleophiles, um, usually if it has like a metal, right, like sodium or potassium, it's going to be a nucleophile. However, it can also act as a strong base. So you gotta look at if it gives you a solvent or not. Also look at the actual nucleophile. Is the nucleophile bulky? If it's bulky, then treat it as a base because bases get bases gets the hydrogens, whereas nucleophiles they actually attach. So if the nucleophile or the base is bulky, it's gonna do a elimination reaction instead, or it's more likely to do elimination reaction. um, Also, if it's like a alcohol like OH, um, that's gonna be a weak nucleophile. But however, it really just depends on your leaving group if it's on what position it's on. That really determines if it's a what kind of reaction it is. Also, SN1 and E1 both happen. Um, it's common for both of it to happen. So um, usually, if I were to pick one, I would pick the SN1 version of it because I substitution occurs slightly faster. It's kind of like 50-50, but well, it's more like 60-40 with E1 or with SN1 and E1. So if it's asking you to just pick one, I would just pick the SN1 product, unless, of course, if they add heat, or if they tell you that heat is being added, then I would choose the E1 product. All right, so mhm, for degrees of unsaturation, here's the formula for it. You just it really changes based on carbons, hydrogens, halogens, and nitrogens. Here's an example. With this one, you would have 4 degrees of unsaturation. Um, yeah, basically, if you have 1 degree, it can either be a double bond. It means that there's a double bond somewhere, or just a ring somewhere. If you have 2, or here, it could mean that we have 2 triple bonds. It just tells you um, if we have double bonds, triple bonds, or if we have a ring. Um, yeah. And then for naming, uh, so find the longest chain that includes a double bond. Make sure the double bond is the lowest possible number. In a ring, it's always assumed that the double bond inside a ring is between 1 and 2. And here's the format of it. So change instead of ane, you do the prefix of like how many double bonds there are, the number of where it's located, and in right here. So examples. So look at the green ones, the green names. So for this one, it would be but one in, because it's on a 1 carbon. For this a ring, because it's always going to be in a 1 and 2 position, you don't have to put a number between um, the or before the "-ine" part. However, if it is like multiple little bonds inside a ring, then you would do the numbers where it's located and then how many "-ines" are there. Here in this case, we have 4, so you put tetraene. Um, yeah, and then just the difference because double bonds cannot rotate. We have the cis-trans um, orientation. So cis is where the substituents are on the same side, trans is where it's the opposite side. Yeah. So however, it only applies if one side has two different um, substituents. In this case, these two are both methyls, so they can't. It's not really. It's not trans or cis because there's no. There's nothing you can really compare it to. And then so there's another convention that is also used, which is the E and Z nomenclature. So you would put E in front of the whole molecule if the heavy substituents are on the opposite side of the double bond, or if it's on the same side, you would put Z. So in this case, bromine is a lot heavier than chlorine. So um, so this would be, you put a 1 on this side, and here um, this methyl is a lot heavier than H, so you put a 1 here, and then you can tell that it's on the opposite sides. That's why this is E. And yeah. So you do that for each double bond that you have. If um, there is like differing substituents. Okay, and also you have to put the number of where um, what you are referring to. So here it would be the third carbon, and E would be like the fifth carbon. So heat of heat of hydrogenation. Another thing, another way you could define that is the amount of energy needed to remove the double bonds. Um, if you have more substituents, you would have lower heat of hydrogenation. Also means that if you have a lower heat of hydrogenation, it means that it's more stable. Um, Also, if it's in a ring, if the double bond is in a ring, if there is ring strain, then it would be less stable, and if it's not, then more stable. So, looking at this, the more substituents would decrease the heat of hydrogenation, meaning it's more stable. If it's just a regular, if it has no substituents, kind of like this, where we just have hydrogens, that would be relatively less stable. And then, oh yeah, here cis is less stable than trans, and then the middle ground is when they're both on one side, which is called geminal. Um, yeah. So when making alkenes, there's really three ways you could do it. They're kind of similar. They're both elimination reaction. They're all elimination reactions. So the E1, E2, it's just called dehydrohalogenation. It means we remove a hydrogen and remove a halogen. Debromination is when you have two bromines. It's like E2, instead of you have two bromines that are being removed. A common reagent is NaI, and acetone. And so, yeah, it's very similar to E2. Um, with this one, dehydration of alcohols, it's treated as E1, where you have an acid here, where the acid will donate a proton to this alcohol, making this acid into a conjugate base. So now you have a base now where you could do an elimination reaction. And when this becomes OH2 plus, um, that becomes a good leaving group. All right. Do you guys have any questions?
All right. Okay, so I guess then we can start. So pretty much let me know if y'all ever want me to stop or if you have any questions or anything, but let's just start and see where it goes. Okay, so the first question is pretty much asking us about anion stability, right? And anion stability is pretty much based on like the carbon the anion is resonant. So the trend is it's a primary is always going to be greater than a secondary, which is greater than a tertiary, and then resonance always takes precedence. All right. So the reason this is the pattern is because anions is giving more electrons to a carbon than it usually can have, right? So we don't want as many electron donating groups on that specific carbon. So if you look at the first molecule, it is a primary carbon. And then the second molecule, it is a tertiary um, with resonance though. And then the third molecule is just a tertiary by itself. The fourth molecule is a secondary. And then the fifth molecule is also a secondary, but with resonance. So looking at this, I guess we can look at the pattern and order it now. Yes, exactly. So for the cation, it would be exactly the opposite because we're electron deficient, right? So we need more electron donating groups to stabilize this cation. But for anion, it is, yeah, it would be primary, then secondary, then tertiary because of the excess of electrons. We don't want the donating groups. All right, so yeah. Okay, so once we start, like, I guess, like labeling each of our molecules, we can then go ahead and start ranking. So let's look at the ones that have resonance. So there's a secondary resonance and a tertiary resonance. And like we said before, we want less donating groups. So the secondary resonance would have number one, and then it would be the tertiary resonance. Okay, and then we will look at all the other ones, and the primary would have the third one, then the second one, secondary would have it, and then the tertiary. So yeah, that's how you do the first problem. Does this make sense? All right, great. Okay, so let's go to the second problem. So it's a bromination reaction. Okay, so like Frank pretty much discussed earlier, during a bromination, what happens is that an intermediate step is to form this radical. So radical is kind of similar to like a cation. Our carbon is going to be electron deficient. So the speed of this reaction is going to be dependent on the stability of the radical. All right. So how you would approach this question is pretty much go through each molecule and label where the radical could be placed, right? So the first molecule is a benzene, and the hydrogens on the benzene are very stable. So they really cannot be even kicked off to produce this radical. So it's like I don't think there will be anything on that one, okay? So I think it would be actually the slowest because of just that fact. I don't think the reaction could occur like that. But then let's look at the other four, okay? So I would say that our hydrogen that would be removed would be right here. And this is a primary, but it is also in a benzylic position, right? Now let's look at the second reaction, second molecule, which is right here. And I believe the hydrogen right here could be replaced with a radical. So then it would be a secondary benzylic. Now let's look here. The most stable spot would be right here, a secondary, because the other ones are primary. If you look at the methyls, they're primary, right? And we would want more substituents. So this is a secondary. And then over here, I would say this tertiary would be the spot. So if we look at all of the molecules that we have now, remember resonance is always the best. So we're going to compare between the secondary benzylic versus the primary. Since it's a radical, it's electron deficient, so it's going to be tertiary is going to be stable than a secondary, which is going to be stable than a primary. So this would be number one, the secondary benzylic. Now it'd be the second one that has resonance. Okay, so now we have the other two molecules, which is a tertiary and a secondary. And we said it's a radical, so we would want more donation, so 3 and then 4. Yeah, so that's how you'd work this problem. Does this make sense? Or do you guys have any questions on it? Yeah, you don't directly mess with benzenes yet. You need like very pretty much cool reactants and solvents and things to get things to move out of that benzene. But the benzene is right now super stable and you cannot remove the hydrogen. Um, okay, so Ranim asks, for the fourth one, why can't you make it one bond over? So for this molecule right here, are you saying? Like the one that's ranked 4? Okay, so why can't you make it which bond over are you talking about? Yes, I can. Sorry, give me 1 second. Okay, I think that may have done it. Can y'all hear these notifications now? Like the pop-up sound? All right, I'm hoping that's a no, but okay, so for the fourth one, why can't you make it one bond over on the right with 4C bonds? I'm not getting your question. Is it, could you try to rephrase the question one more time?
I think she said they're asking if why can't you put each.
Yeah. Oh, okay. So if you look at this carbon right there, right? So in a bromination reaction, we need a hydrogen that needs to be replaced by a radical, right? So if you look at this one carbon, it doesn't have a hydrogen molecule even to react with. So that's why we couldn't use that carbon by itself. Does
Oh,
that make sense?
yeah. I think I think they might be saying can you like methyl shift it? That is what
Uh,
isn't
I don't think you can methyl shift it because it's not like it's like a SN1 reaction where we have a whole leaving group and when there's like a whole stable cation being formed. Um, I think that's like kind of more for SN1, not for a radical formation, if that makes sense. Did that make sense, Raneem? Did I answer your question? All right, yeah. So the point is that there's no hydrogen to like really do it. Okay, so Tabarik says compounds 2 and 3 are faster because of resonance, right? Yes, exactly, because of resonance. In all of OCHEM, you will see that resonance really does take precedence a lot of the time, especially since there is a radical. It can pretty much do resonance with the whole benzene ring, and that's like very stable, making it faster. But yeah. All right. So let's move to the next question. Okay. Okay, so it's pretty much asking for SN1 reactivity. And in SN1 reactivity, the main goal is to look at our cation, all right? So we're gonna go ahead and just label each one of our leaving groups and see what type of carbon it's on. So the first molecule is on a primary, but then remember, okay, so one thing you can notice is that there's actually a bulky group. All right, bulky. All right, this one is a secondary. This one is a tertiary. The fourth molecule is a secondary. And then the fifth molecule is also a secondary, but it has resonance. All right, so for cation stability, what our goal is, we always like resonance first. Resonance is gonna always win. And then we have electron deficient carbon, right? So we want electron donating groups. Hence, a tertiary is going to be more stable than a secondary, which is going to be more stable than a primary. And then if you have a bulky group, that's going to be last. That just kind of prevents the nucleophile from attacking. That's why the bulky is last. And oh yeah, for that second molecule, this molecule too, there is a bulky group. I just didn't get to write it. Okay. All right, so now let's start, I guess, start labeling all of it and ranking it. So first we look for resonance. Our last structure has resonance, so we'll get that, give that 1. Then let's look at if there's any tertiaries. Yes, there is a tertiary, so let's give that 2. Then let's look at secondaries, which is 3. Now let's look at our first 2 molecules. Both have a primary carbon and a secondary carbon, but both of them have bulky bases. So the secondary one is still going to be more stable than the primary because of the cation. So this is going to get 4, and the first molecule is going to have 5. Does this make sense? All right. Okay, so let us go to the next page. Are y'all good with this page? Like any last minute questions? Because I'm not sure if it's gonna like save like the writing when I leave this page. That's okay. Okay, I'm gonna leave it. Let's see. Okay, so now let us look at this page. So it's pretty much like, okay, so we first look at the reactant, which is Br2 and HB, okay? So when you look at the reactant, you can see that it's like one of those bromination reactions where the whole radical is formed. So remember, bromine is very selective. So there's only going to be one spot. You're going to find the most stable hydrogen spot, and then you're going to replace it with a bromine, all right? So we're going to look for the most stable spot. If you look at this first molecule, it's right here, right? And you can then pretty much take the hydrogen that was there. It's gonna, I'm not sure if you guys will be asked for like mechanism, but pretty much a radical forms and then a Br replaces it. So let me just draw this out. Excuse my mediocre drawing. Oh my god. Okay. Okay. But now we have a Br right here. Okay, so there was a hydrogen, the hydrogen becomes a radical, the radical then um, gets sucked in by another bromine. So that's pretty much that. Did that make sense? Let us go to the next problem. So here we still want, if we still want the most stable spot, right? Wait, why was the Br out there again? Which one? The bromine that's on the like the actual product right now? Because it's because it's tertiary. So the order for like bromination would be, since we're trying to find like a cation, or I'm sorry, a radical, it would be tertiary is going to be greater than a secondary, which is greater than a primary. So if you look at all the hydrogens that's on this molecule, there's a lot of secondary there's a lot of secondary hydrogens, right? But then right here there is a tertiary hydrogen. Hence, we can replace that tertiary hydrogen with the bromine. Did that make sense? Okay, great. Um, Okay, so now let's look at this molecule right here. Okay, so the other tertiary carbon would be just as likely to bromate. Yes, exactly. It's a very symmetrical molecule. So, wait, what does A or E mean? Oh, axial, equatorial? I think it would still be the same, I believe. Yeah, so I think it will still be the same because it's a very symmetrical molecule. So you could literally like split it in half, or like take it and like, do a whole 360, you'll see the same exact molecule for that, if that makes sense. So you could do either or. Both work. Okay, so let's go to B. So looking at all the molecules, hydrogens, okay, so we have this top like three metal things, but I guess don't be confused. There is no hydrogen over there for us to replace with the radical. So we would have to choose the hydrogen that's located right here because it is a tertiary. And remember, we like the most electron donating possible for this reaction. So pretty much that hydrogen gets replaced with a bromine. Okay. Dun, dun, dun. All right, and then there is going to be a bromine right here. Okay, so did this one make sense? This was pretty simple, straightforward. All right, now let us go to C. Okay, so now we have, remember, it's a benzene. We cannot work directly on the benzene, but we can work around the benzene. And if you look, there is a hydrogen right here, and that's a secondary. A secondary is obviously better than like this hydrogen on the side because it's primary. And additionally, that hydrogen also has a benzylic position. It's very close to the benzene, hence it can do resonance. All right. So you can pretty much put the bromine on that one. And if you look, there is an ethyl on the other side. This molecule is pretty symmetrical, so you could do either one. It doesn't really matter which one you choose. Okay, so that's how this molecule will look. Now we have D, which is asking us about kind of the same exact reaction. Only thing is that our reactant changes. Our reactant is now chlorine. Do you guys know what the difference between chlorine and bromine, like what happens if it's chlorine doing this light reaction instead of bromine? Yes, exactly. Chlorine is not as selective. So we're not going to just have like one product. There could be multiple different products that we can choose, right? So pretty much we can just choose where all are the hydrogens and um, do pretty much substitutions for each one of them. Okay, so first thing I guess would be to identify where these hydrogens are, right? So if you look at this molecule, there is a nice line of symmetry down here, right? And then you could do that same vertically too. You could do the whole division vertically. So pretty much all these three methyls on the top, right? They all had the same exact hydrogen. So we can choose one hydrogen we want out of it, because it would be like if we even if we did all the other ones, it would be similar because of symmetry. Okay. So we have that hydrogen that we could replace. Then we have this hydrogen that we can replace. Okay. And then we also have this spot right here, okay? So pretty much what's going to happen is that means that we can have three different molecules, all right? So let me know if y'all are not like following, but this is because of the fact that chlorine is less selective, hence we can have more than one, I guess, product. All right. Oh, this. Sorry, this is supposed to be a chlorine. All right, so this is our first molecule. And I guess I'm just doing this for like fast sakes, but yeah, this should still have its veg and stuff, or its dash and anything. It doesn't get affected. Um, all right, so that's our first molecule. Now let's do the second one. Okay, so we can put the chlorine right here, replace that hydrogen in the middle with the chlorine, and then the top still remains the same. All right, so that's that one. And then all right. So that's this. Does this make sense? Any clarifications needed for that? I'm hoping that makes okay. It makes sense. All right. So now let's just keep going. So it says of the reactions listed above, which will react the fastest. So remember, because chlorine is less selective and it's just easier to react with, chlorine is going to be the faster reaction. So it's actually going to be D. Although if you look at the positions, yeah, you are right. Like the C might have the secondary benzylic. At this point, we have to also look at what is being attacked and what is like the characteristic of like bromine versus chlorine. And chlorine is more reactive, hence D would be the faster reaction. Did that make sense? You guys can just say okay. I guess you don't have to like always reply if you don't want to. Okay, so if y'all are good with this one, so all chlorine reactions occur at the same rate. Well, it would be more so like once we're comparing just chlorine with chlorine, you know, then like you would do the whole tertiary, secondary, primary thing, and tertiary will obviously be faster. But when you're comparing between bromine and chlorine as the reactant by itself, then chlorine would be the faster reaction than bromine. Yeah. So I don't think you have to compare between the three molecules, like, or between the three products we're making. Because, yeah, then technically the tertiary would be the fastest. But, yeah. All right. So let's go to the next one right now. All right. Okay. So let's see. What are we trying to do here? Consider the structure of the following solvents when answering the question and see what would be the effect of the rate of the reaction. Okay, so we're trying to change solvents pretty much and see what's going to happen. Okay, so let's look at the solvents that we have right now. Okay, so DMF. DMF is a polar aprotic. DMSO is also a polar aprotic. And then methanol is a polar protic. All right, so now when we're looking at this reaction, the first thing is that I guess we need to know some trends, okay? So for SN2, like polar aprotic, and then for SN1, we like polar protic. Okay, so I'm trying to just use a bit of text so that it just looks a bit cleaner, but yeah, so let's go ahead and go to each molecule and see what type of reaction is happening, okay? So for the first reaction we have right here, what's happening is we have a primary carbon with a very strong nucleophile, right? So if it's a strong nucleophile and a primary, that would be an SN2 reaction, right? So now they're saying that what would happen to the reaction if the solvent was changed from methanol, which is protic, to DMF, which is aprotic. So remember, SN2 reactions like aprotic, right? So then the reaction would become faster. Okay. I'm hoping that made sense. We're going from protic to aprotic, and hence the SN2 reaction does get faster. So now let's look at the next reaction. So what type of carbon do we have? We have a tertiary, right? But we have a very strong nucleophile, right? Although we have a very strong nucleophile, and I know N3 usually goes with SN2, the fact that we have a tertiary like automatically brings it to an SN1 reaction because SN2 it's just too like hindered and you can't really what do you call it, do a backside attack. So now they're asking in the question, how would the rate of the reaction change if the solvent was changed from methanol to hexane, right? So methanol is polar protic, right? So we're already at a very desirable state, and then hexane is non-polar, right? So this would actually decrease the rate. It's non-polar. I think the reason we would not consider an E2 is because I don't think N3 is a strong base. I think it's more of a strong nucleophile. I think it's a weak base, if I'm remembering correctly. Did that make sense? I am hoping it did. So strong bases prefer elimination reactions. Yes, exactly. So most of the time, like I remember somebody asking the same question about like, how do you know if it's going to be like a elimination or a SN reaction with like a strong base? If it is like a strong base and you have like a primary or secondary, then yeah, or a tertiary or secondary, it's mostly always elimination. Yes. And then a nucleophile is what does like substitutions, and a base is what does elimination reactions. All right. Okay, so now let's look at the last one. So here we have a heat reaction, and so our leaving group is Cl. Cl is on a primary carbon. And then this is kind of a cool molecule because the nucleophile is already on the molecule. It's a pretty good nucleophile and it's a primary reaction, so I would give it an SN2. Okay, so what happens is usually it's going to just come in attack right here and pretty much kick out the Cl, if you guys were wondering. But for this SN2 reaction, the question's asking how would the rate of the reaction change if the solvent was changed from hexane to DMSO? So hexane is nonpolar, DMSO, like we said above, is aprotic, right? Polar aprotic. Hence, I think the reaction will get faster. It will increase because obviously aprotic is more favorable. So that is this page. Did it make sense? All right, so if y'all don't have any questions on this page, I'm gonna move ahead to the next page. Okay, so now we have all the reactions, right? So this is my process with it. I'm hoping that it helps y'all out too, but pretty much just go at it very systematically and see what you have. So here you have a look at the actual molecule. You have a tertiary carbon, right? This bromine is on this tertiary carbon because it's attached to the CH3, the CH2, CH3, and obviously a back carbon too, okay? Now we look at the nucleophile or the base, whatever it is. It is a strong base, right? Because it's OCH3 minus. So if you have a tertiary with a strong base, then it's usually an E2 reaction, right? So now that we know that it's E2, one of the criteria is that it has to be anticoplanar. If you look at the molecule, it's already anticoplanar for us, the Br and the hydrogen, right? So that makes it pretty easy for us, and we can act like we're forming a whole double bond. And this is how the molecule would look. And there would be a double, let's see if I can erase that, or I can try to draw a better double bond for y'all. Okay, but yeah, so this is how the double bond would look. Did this one make sense in the fact that Br and hydrogen is like completely anticoplanar, and that's why it makes it like more driven towards E2 than any other? All right. Okay, so now let's look at B. Okay, so we have, again, let's go label out what we have for each, what's it? Bromine on. So it is a secondary carbon, right? Because there's a hydrogen on the right, there's a CH3 on the left, and then obviously it's connected to a CH3 on the, or the C in the back. So that's a secondary carbon. And then we also have a strong base, or it could be also a strong nucleophile. Okay, so even on the top, like if you guys wanted to write it, you could do like for that first A question, it would be a strong base and strong nucleophile. The reason it became E2 is because tertiary carbon, okay? So here we have a secondary carbon, and then we also have a strong base versus strong nucleophile. Since it's a secondary carbon, it would go to SN2. All right, so for SN2 reactions, it's going to be a backsided attack, right? So how you would want to do it is, let's see, you would want to make sure that there is inversion involved, okay? So the way I look at it is that the bromine gets replaced, right? And it's like the OCH3 comes in and has like a whole backside attack, right? So then the OCH3 goes right here. Only thing is that there has to be an inversion. So how I do it is I look at the leaving group from before, which is bromine, and then I go clockwise from it. So from clockwise, it used to be hydrogen, right? So when we make the product, the clockwise product from OCH3 should not have hydrogen. It should have the other molecule. So it should be CH3 if I go clockwise. And this is just for the inversion. I'm hoping that I explained it decent. Let me know if it's confusing. All right, and then we obviously have the back carbon. Okay, so did this make sense? This is honestly the weirdest part is the whole inversion. Okay, so did you have like a question that was specifically like, um, that, do you just want me to try to explain it better? Yeah, so pretty much act like, for inversion, right? It's like a backside attack, and that's why I drew my arrow like this, okay? Can you guys see the arrow, can you guys see my mouse? So then we act like the OCH3 is in the back, right? Or like in the bottom. Yeah, so you flip the front carbon upside down. Only thing is that you need to make sure that there has to be inversion. So the only way we can do that is we can do like we can compare, right? So on the in the original molecule from bromine, clockwise, I could see there was a hydrogen, right? So if it has to be like pretty much then for the actual product, it has to be that hydrogen is counterclockwise from the new nucleophile. And the only way you could do that is through this. If that made sense. I'm sorry, y'all, if that was a bit confusing. Okay, so I'm hoping that was not too bad of an explanation, but let's go to the next problem. So here we have, oh, sorry, give me a second. We have this molecule, right? Bromine is our leaving group, but it is a secondary. Now we have our nucleophile or base. I think it's a strong base. The only thing about it is it's super bulky, right? Because it's a OCH3, this is how it would look. There would be three methyl groups, making it like this part is super chunky, and hence it would have to go towards like a E2 reaction. Okay, although it's a strong base, it would be an E2 because of the fact that it's very bulky. Okay, only thing is that since it is bulky, we prefer the Hoffman product. So when we're stealing the hydrogen, we have two options here. We could either steal from this top hydrogen to make our double bond, or we could steal it from this hydrogen, right? The thing is, because this is a very bulky base, we have to choose this hydrogen right here and make the least substituted. That's because this whole big strong base is so bulky that it wouldn't have the space to go and steal the H from here. Okay, so then the molecule would look like this. So the CH3 would remain unharmed. All right, and the double bond would be formed right. Oh, uh, if somebody's trying to change the page, will y'all not? So that we can draw on it. But this is how it will look. All right. Um, hey, I don't know if any of y'all are. Uh, I'm not sure if somebody's trying to change the page, but will y'all not change the page so we can work the question we're working on? And if you do have access to the drive, I guess, with the actual doc, I can post it so that you can get access to it. Here, I'll put it again. Okay, so that's for this reaction. Did this make sense about how it is a Hoffman product because of the fact that it's a bulky base? All right, so now let's go to the next problem. So this is a decontamination reaction, all right? So this I is just floating around as like a very good base or nucleophile at this point, and it's going to do like a very similar reaction to E2. What it's going to do is it's going to steal the bromine, right? And then the electrons that are holding the bromine into the molecule is going to drop down, and bromines are pretty good leaving groups on its own, right? So this is going to be kicked out, and it's going to leave by itself. So then what you're going to have is a product where both the bromines are gone, and then there's going to be a double bond right here. All right, did that make sense? Give me a thumbs up, give me an okay, something. Um, all right. Okay, so yeah, so that one was D. Now let's go to E, all right? So the process is look at your reactant, find what type of carbon it is. So this is on a secondary carbon. That's pretty good. AgNO3. This molecule is pretty specific for what we call SN1. Okay, so whenever you see this molecule, just go straight towards SN1. All right? And then yeah, so pretty much the first towards an SN1 reaction is you form this cation, right? Carbocation, all right? And it is a secondary carbon. Now, the only step that you do have to look at is you look at the neighbors and see if there's a better cation position. So remember, cations like tertiary and like resonance and all of that, right? So in this, there could be another intermediate where is a hydride shift, okay? So that we can move the carbocation onto that tertiary position. So we're going to have, okay, and the hydrogen that was there is now here, and the carbocation is now here. All right. So that is what a hydride shift is. So anytime you have like example like a neighbor like as a like a tertiary carbon and you have to like choose, okay, you can either do a hydride shift or a methyl shift, and the way you choose is you always look at the one that has a smaller mass. So if there is a hydrogen, go and do the hydride shift first. If there's only like 3 methyls there, then you can do the methyl shift. All right, so now let's go ahead and attack the carbocation, and it would be with the OCH3 right here. All right, so that would be this molecule right there. Did this make sense? All right, so let's keep going. Okay, so in this molecule, this is pretty basic. We have a primary carbon, then you look at the nucleophile, and it is a strong nucleophile, right? Because it has a negative charge. And usually, most of the time, a primary carbon usually goes towards an SN2 reaction. So all you do is a good, nice little substitution with this SC3 right here. All right, now let's go to the next one. So we have, this one's a bit more weirder, but we can do it. So we have this carbon, right? This bromine is on a pretty much a primary carbon, right? Only thing is that if you look at the neighbor, this is like a, what is this? This is like a quaternary structure. It's very like hindered, right? So we can't directly go towards this like an SN2. And this is a strong nucleophile. Because it's hindered, we're going to go towards an SN1 reaction, okay? So we're going to form the intermediate cation. Okay, so we have this cation. So remember, I said that we could always look at the neighbors and see if you have a hydrogen, great, we can do a hydride shift. In this situation, you don't have a hydrogen, you actually have a methyl. So then you can do a methyl shift. And methyl shift. Okay, and that will give you this. 1 second. So now this carbon is, this carbocation is on a tertiary atom, right? And that's very good. So Now you could do a oh, okay. So because it's an a strong base, right? And you form this carbocation, you could do a an E1 reaction. I'm sorry about that. So technically, we would have to form like the most stable double bonded situation. So you could do it right here because it has three. Like you could, what do you call? You could pretty much act like the OCH3 is going to act like a base and go and attack this hydrogen right here. Um, Sorry, give me 1 second. For page 5 on G, why do y'all do E1 instead of SN2? Oh, because of Frank, are you here?
Yeah, I'm here. Number
Do you
three, right?
mind? Do you mind telling us for I think it's G, the one that we're actually working on,
Yeah.
that she was wondering why it's a E1 instead of SN2.
Right.
It would be because of like hindrance, right?
Yeah, you don't have anticoplanar. That's why.
Oh, and the fact that you don't have, yeah. Well, for SN2, you don't need anticoplanar. It would be
Oh
more
wait.
the fact that there's hindrance.
Yeah. Yeah.
Ranin, did that make sense too? I guess like we're doing the same problem for Tasneem and you, but it's more so because of that. It's the fact that like OCH3 is still a very strong base, right? And the fact that once we form that cation, I think it can still act as a base. It's just going to be going through the E1 mechanism. Okay. So not E2 because there's no hydrogen on the adjacent carbon. Yeah, no, yeah, exactly. There is no hydrogen on the adjacent carbon. And it's also a primary carbon. So like for E2, usually we like more like tertiary and secondary, I would say, than a primary. Okay. Do y'all have any more questions on that one? I am hoping not. So let's keep going, I guess. So for H, we have this Cl, right? And it is on a secondary carbon. And I is a very strong nucleophile. So that means it would go towards SN2. Sorry, let me just erase this part really quick. Okay, so an SN2, so then it would become like this. Remember there's inversion, so this I is going to go ahead and do a backside attack, kicking the Cl out. All right, so that's that one. Give me 1 second, y'all. Let me just plug my charger. All right, so I'm back. Did that one make sense? That was pretty straightforward, I would say, compared to the other ones. Okay, so Tabark says if the compound is not bulky and it is a strong nucleophile, it will be SN2 for primary and secondary carbons. Yes. Unless it's like, make sure you also look at the molecule, and if it's like a tertiary carbon, it would not be an SN2. Oh, yes. You have it all covered. Yeah, that's exactly it. All right, so now let us go ahead and continue. All right, so this bromine is on a secondary carbon. This is a strong nucleophile, and this would become an SN2 reaction. And remember, there's always going to be inversion for SN2, right? So this bromine that was now a dash, now the NH2 that's going to join is going to be on a wedge. Okay, I'm hoping that this made sense. All right, and now let's go to the next one. This is a tertiary, right? And it is a pretty weak nucleophile. Anytime it's like an OH, it's usually like a weak nucleophile. So this is going to be an SN1 reaction. Obviously, we have the first, we do have a cation forming. The cation is on a tertiary carbon. Remember, cations already like tertiary, like a carbon, so we don't really have to worry too much about the whole methyl or hydride shift, so we could do that. So remember, so anytime it's SN1, it could also be E1 too. So there could be two ways that this goes. So for if it was an SN1, what would happen is we would go ahead and do the whole OCH2 situation. Okay, so this one was for SN1. And then if it was E1, right, we still have this molecule, and then we want a double bond. We want the most substituted double bond. So then we would form it right there. All right, so that's how this molecule would look like. Did that make sense? All right. Okay, so that was that page. Now, if y'all are good with, I guess, the basics of the reactions, let's try going to the next page. Let me know if you guys have any questions. Okay, so here we have pretty much, I guess we could just talk about this more so. Okay, so the gist of it is they're just asking us what's going to happen to the rate of SN1 and SN2 for each reaction, okay? Or with each change. So let's look at the molecule that we have right here. So we have a secondary carbon, and it's still a secondary carbon, okay, for this main molecule. Now let's look at A. It says that the chlorocyclohexane is changed to 1-chloro, 1-methyl cyclohexane. So that means our reactant is going to look like, ooh, I'm sorry y'all for my bad drawing, but it's going to look like this. Right? So when we do that, now it has changed towards a tertiary, okay? So I guess now the question is, what's going to happen to the rate of the reaction of SN1 and SN2? SN2, do y'all have a guess? Would it increase or decrease? Yeah, it would decrease. What would happen to the rate of SN1? Remember, so it's like we're trying to form a carbocation, right? Yeah, it would increase. It would increase. Compared to the secondary, the tertiary would be more stable. All right, so now let's look at B. The chlorine is now replaced with iodine. Okay. Either ways, when comparing chlorine and iodine, which is a better leaving group? Yeah, so iodine is a better leaving group, and this means that both SN2 and SN1 would both like be faster. The rate would increase. All right. Now let's do C. Sodium bromide is replaced with sodium iodide. Okay, so now we have um, bromine or bromide was the first nucleophile, right? In our original molecule, bromide was the original nucleophile. And then now we have iodide, which is a better nucleophile. Any guesses? Um, yeah, it kind of does have, it does have to do with the chart. Yes, it does. Okay, so iodide is bigger, okay? So it is a better nucleophile than bromide, if my memory serves me right. So what's going to happen is that for an SN2 reaction, our nucleophile does matter, okay? So for SN2, the rate will increase, okay? That's what it's dependent on. It depends on the nucleophile, all right? But for SN1, the rate actually doesn't depend on the nucleophile. It depends on the cation that's being formed. So no matter how much we change our nucleophile strength, we're pretty much waiting on that leaving group to leave so that we can have the reaction. So this is kind of like a tricky question, but for the SN1, the rate does not change. Did that make sense? All right. Um, Okay, so now let's look at D. The temperature of the reaction is that it's run in is raised. Okay, so heat is pretty much really good for both reactions. I think it's just like a known fact. It just allows pretty much all the molecules to reach that activation energy faster. So yeah, SN1 and 2 increase. Okay, and then for this one, for E, okay, so we used to have a secondary carbon, and now what they're doing is we have a secondary carbon, but it has resonance. And remember, resonance always takes precedence, and that will help both the SN1 and SN2 reaction. Did that make sense? All right. Now let's go to the last one, okay? The solvent is changed from methanol to hexanes. Okay, so remember, methanol is polar, right? So SN2 likes polar aprotic, right? And then SN1 likes polar protic. So for methanol, methanol is polar protic, right? But it's still protic. Hexane, on the other hand, is nonpolar. Hexane is nonpolar, and that's like pretty bad comparatively to it's not even polar, right? Although for SN2 it's not like aprotic, it's like not polar at all. So it's a bad situation. So for SN2 and SN1, it would drop the rate. Okay. Does that make sense? I just want to make sure that you guys are like, I guess, coming along with me or following along. All right, so that was that. Uh, okay, yeah, let's come back to this one. Let's go to the next one. And then we'll choose which nomenclature ones that we want to do together. But so this question is pretty much asking of the following isomers, which would be expected to be the most stable. All right. So there is a trend to this. I'm pretty sure Frank already talked about this. So the trend is you have to have the most substituted, right? So four substitutions is better than three, and three substitutions are better than two, and then one. All right. So pretty much the ranking is 4, 3, 2, 1. All right. And so we can look at each molecule and rank it depending on how many substitutions it has. So this first molecule has two, right? two things that it's attached to, the double bond. And then for the second molecule, it's attached to three things, the double bond. And now the last molecule is attached to two things again. So remember, we always like the one that it's most substituted. So this is the most stable. Okay. All right. Now let's look at the next molecules or the next question. So this first double bond, it actually only has one substituent, and the second molecule is attached to two things, and the third thing is also attached to two things. All right, so now we're kind of like at a spot where we have to see which is more stable, depending comparing the two molecules that have two things. All right, so this is a trans, and the first molecule is cis, or sorry, the second molecule is cis. And if it's trans, trans is more stable than the cis, so it would be this one. Okay, and for the last one, let's see, it has three things that it's attached to the double bond. For the second molecule, it has two things it's attached to. And the third molecule, there is also two things. So remember, we like more substituents and attachments, so it would be the first molecule. Yeah, so did that make sense? So the only weird one is the trans versus cis. Trans is more stable than the cis if it's like you come to like a double bond and both of them have two attachments. All right. Is cis opposite? Cis is on the same side. So if you look at the attachments on the double bond, okay? So cis means same side. So both the methyl groups are on the same side, right? The second one is trans, and it's in opposite sides. So trans is opposite. So you're looking at what it's attached to. Yeah. All right. So I think that's mostly it. Like, you guys can go back and work on this by yourself in your own time. I feel like it might take a long time, but we do have the key posted, right, Frank?
Yeah, the key, I should have it post. It should be in the link as well.
Yeah, so we pretty much worked through everything is the nomenclature, just work through it one at a time. And yeah, if you guys want to check, you guys can always check the key. Other than that, did y'all have any other questions? I'm sorry if I rushed it or if I was confusing. Any questions? All right, I'm glad to hear that. I wish y'all luck, and feel free to come to peer tutoring throughout the week, and we're always ready to help y'all. So good luck.